Hello everyone. Let's continue from where we stopped last time. So we were looking into a setup timing analysis of a flop to flop, from one flop to another flop. So we had this one flop, we had this another flop, and the combinational delay from this point till this point is, let's say it's called as theta. And the specifications was given to us that the clock period was 1 nanoseconds, and hence the clock frequency is 1 gigahertz. So the requirement that comes to us is that the combinational delay that you see over here should be less or equal to t. Basically the combinational delay should be less than your time period. That will ensure that the circuit will work at 1 gigahertz. If theta exceeds the value of t, that is, if the combinational delay exceeds a clock period of 1 nanosecond, it means that the clock period itself has to be increased, and as a result of that you see a drop in the frequency, because an increase in the clock period, the inverse of it is the frequency, and the frequency will drop. So that was what we saw in the last time. Also we saw that this particular analysis was done with a clock, with an ideal clock. By ideal clock we mean that there are no buffers. It is just as good as a zero wire load. There is these are not physical wires, and the clock tree is not built. We went with an ideal clock. Now what we'll do is we'll consider that this particular clock has already been built like this. That is, we have one clock buffer which is placed over here, there is one more clock buffer which is placed over here, and there is two more clock buffers which is placed in the capture flop clock line. So this is basically a clock tree. To get into details of building of this clock tree and all those things, we have a separate section of videos called as clock tree synthesis. You might want to have go and have a look into that, because that explains each and every detail of clock tree synthesis. Right now we'll now look into what is the impact of timing when we add this clock buffers. Okay, so let's look into that. So when we add this clock buffers, what does that mean? That does mean that when the clock which is supposed to arrive at 0th clock pulse will now not arrive at 0, but will arrive after 1-2 buffer delays at the launch flop. Okay, because now we have these two clock buffers and the clock is now propagated. It's not ideal, it's a real clock. Similarly, the clock which is supposed to the clock edge which is supposed to reach over here at tth clock time, it will now reach at 1 t plus 1 2 3. That is, it will reach somewhere over here. So that makes analysis a bit real, and as a result of that, when we look into the equation, the satisfying equation for this kind of circuit, it's a bit different. Let's look into that. So now the theta, your combinational delay theta, will extend till the clock port. Okay, so theta will be theta. No, it is no more theta. It is basically theta plus 2 plus 1, or theta plus 1 plus 2. Okay, and that should basically theta plus 1 plus 2, yeah, that we have mentioned, and that should now be less than, it's pretty obvious, because initially it was t, but now t is not arriving, the clock pulse is not arriving exactly at t, but it is arriving somewhere over here. That is t plus 1 plus 3 plus 4. Okay, so the combinational delay plus 1 plus 2, that is the clock delays, should be less than t plus 1 plus 3 plus 4. This is basically your satisfying equations. Just after looking into this circuit itself, we have developed this particular equation. This is what your combinational delay should look like. Okay, so 1 plus 2 will be called as this is 1 plus 2, since it's present in the launch flop clock path. It will be called as launch flop clock delay, which let us call it as delta 1, and 1 plus 3 plus 4, since it is present in the capture clock path, let us call it as capture clock delay. Okay, so let's call it as delta 2, and the difference between delta 2 and delta 1, the more difference of delta 2 and delta 1, it's called as skew. So the concept of skew and all those things has been already been talked about in a separate section, which is clock tree synthesis. Let's brief things about here. So now what we'll do is let's graphically install this delta 1 and delta 2 on this particular waveform and see what is the impact. That will give a clear picture of what's happening. Graphical way is always the best way to understand things, so that's why we have taken this approach. Let's put this delta 1 over here. Okay, so delta is the zero, the pulse which was supposed to come at 0 is, it has now got shifted by an amount delta 1. Okay, and the clock pulse which was supposed to come at t is now shifted by an amount which is called as delta 2. So this will be your realistic graph which for this particular circuit, and this will be your satisfying equation or satisfying condition for this particular circuit. Okay, so also along with this particular equation, we have some more uncertainties and some other things. So basically there is something called as setup time, the flop setup time. So there is some amount of time that is required for this particular flop to capture the data and to settle it down somewhere at the center. So that because flop is nothing but build of MOSFETs, build of transistors, so each and every transistor will have some amount of delay, and as a result of that you will see that there is some finite delay, there is some finite time that the flop will require when it receives the signal to process the data. So once some data comes over here, the flop needs to process it, and there is some amount of processing time that goes within the flop, and that processing time, let's call it as setup time S, and let's consider it as a very low, that is 10 picoseconds, because over here we have only MOSFETs and they are like very fast. Okay, so let's assume that the setup time is 10 picoseconds or 0.1 nanoseconds. So that much amount of time is needed for the capture flop after receiving the data, so that time has to be accounted for. So what we'll do is we'll take that time and subtract it from your final equation, that is from this point. Okay, that is one thing. And second thing, there is something called a setup uncertainty. So uncertainty is basically, since we are looking only at 2 flops. So for example, if you had thousands of flops which are spreaded across the circuit, so each and every flop, it is very unlikely that the clock period which is supposed to arrive at t plus delta 2 will arrive exactly at t plus delta 2 for each and every flop. And the reason for this is the on-chip variations that we have. So basically on a chip we have different kinds of process variations. A chip is not a flat surface, it's a varying surface. It might have got some, it's like a road. So road is never a flat, it has got some pebbles, it has got some speed breakers and all those things. So that's why you can't predict a time required to move from one end of the road to other end of the road. It might be varying for 2 different kinds of roads. So similarly, the clock signal itself will have varying roads, will have varying paths. So the time required for this clock edge to reach at this capture flop will be different from the time required for the same clock edge to reach a flop which is sitting at this particular corner of the chip. Because of some variations. Okay, so we have to capture that uncertainty, that particular values. So it's not certain that the clock period will arrive exactly at t, so we have to account for that uncertainty as well. So we are taking that as 90 picoseconds period over here. 90 picoseconds will be accounted for the uncertainty. This is only the uncertainty, and there are other ways of modeling this thing, like on chip variations and so on things. We'll be looking into that in a STA lectures, not over here. So those uncertainties will be accounted for over here. Yes, and also there is also one more point where the clock, it is at every clock cycle, this particular clock edge is supposed to arrive at exactly at t, but it might arrive somewhere before t or somewhere after t. in the same clock, in the same flop, when it receives multiple clock signals, the same clock edge might receive at t, might come somewhere beyond t, and somewhere before t, because of, again of the variation on the chip. So all these things has to be accounted for, and uncertainty is the one that will help us to calculate that. For there are other ways where on chip variations and D rates and all those things comes. We'll talk about that in a separate section. So these two parameters, that is the setup uncertainty 10 picoseconds, setup time as the 10 picoseconds, and uncertainty as 90 picoseconds. So these two has to be accounted for before the clock period. Let's do that. So this is your setup time, which is something at the final edge of the clock. You have to subtract that amount of setup time, and there is setup uncertainty. We need to subtract it from the final arrival, from the final clock edge. So your equation becomes t plus delta 2 was already there, minus the setup time, minus the setup uncertainty. Okay, so this becomes your final defining equations for your setup analysis. Now what we are learning over here is the impact of crosstalk delta delay on timing. So in this particular circuit, what we'll do is we'll introduce crosstalk. We'll try to introduce crosstalk and see how this particular equation, basically when we introduce crosstalk, how that crosstalk impacts this equation, and this equation gets affected because of crosstalk. Basically this condition is that the theta plus delta 1 should be less than t plus delta 2 and all those things, but how the crosstalk will make the left hand side go higher than the right hand side. Let's look into all these concepts in the next video. Thank you.